Hi, welcome to the wonderful world of physics. It's getting to that time of the year where there's forest fires, overachiever mixtapes dropping, but there's one thing that saves every life if there ever is a fire: a smoke alarm. It saves 20,000 lives a year on average, but does anyone know how it works? Guess what? I'm going to teach you today. Just remember, safety first. See, let's test this bad boy out. I could either use a lighter, or I could use a little bit of chemistry, make a smoke bomb. It will combust into a lot of flames from the gas inside the ping pong balls, which in turn will cut off the laser between the opto interrupter, aka the photo gate, and set this thing off. Let's do this. Mom! In a normal optical chamber for photoelectric smoke detectors, you have an infrared light, a photocell diode, and baffling around the outside. The key is that it's light tight, but not airtight. This is so smoke can get in, but no ambient light carrying IR can actually get in to affect the photodiode. Once smoke enters the chamber, it's going to refract the IR light being shot off by the LED into the photodiode, which in turn is going to drop the resistance of the system, sending the current sky high, which is going to set off the piezo buzzer. In order to understand piezo buzzers, we have to understand piezoelectricity. In normal piezoelectricity, an oscillating pressure, which usually originates from a crystal of some sort, converts mechanical energy into electricity. However, in piezo buzzers, it's the exact opposite. Inside the housing, there's a brass plate, piezo ceramic plate, and an electrode. In order for the buzzer to make a sound, a high enough electrical frequency must be delivered. This originates from what I just discussed. Once the photodiode gains energy from the IR light, it increases the current, which also increases the electrical frequency. This frequency is delivered to the oscillating buzzer. This increases the energy and converts it into sound pressure, which is measured in decibels. In layman's terms, the sound pressure is that O2 familiar, extremely loud sound most people hate. The buzzer I used operates at a max of 102 decibels. For those who don't know, the highest threshold in a work zone you can work under is 75 to 80 decibels before you have to wear ear protection or sign a waiver. I could go on for hours about how this circuit works, and you'd probably still not understand. Let's just be thankful it's direct and not alternating. This detector would be the industrial engineers of the detection world if it wasn't for the opto interrupter. Kind of stupid. An opto interrupter is the fancy term for a photo gate. It works by using an LED that creates a beam shooting straight into the phototransistor. If anything, and I mean anything, breaks that beam, the system will set the alarm off. Before my mom decided to throw water on the $50 worth of electrical equipment, I was going to show how sticking a piece of paper between the slit would set the alarm off. Now that we understand how that works, we can look at the bigger picture. When the smoke enters the slit, it breaks the beam. As a result, the phototransistor stops working, and transistors 1 and 2 conduct to activate the rest of the circuit, which sends a voltage to transistor 3. Due to this, SCR current goes sky high, which at this point, the gate terminal of transistor 4, which receives a positive voltage through our 4th resistor. All of this produces enough electrical frequency to convert the frequency into sound pressure, setting the piezo buzzer off. For those who don't grasp concepts well, the beam is interrupted, but it's cool because the transistors 1 and 2 got their back, so they call the homies to do them a favor. Transistor 3 knows this other guy, transistor 4, he gives him a call, and a transistor 4 knows a top dog for the electrical mob who can send a message forever imprinted in your eardrums, the Godfather, Mr. Piezo Buzzer. And that, in a nutshell, is the conceptual physics behind this system. Resistance total is measured by the equation 1 over resistance 1 plus 1 over the resistance 2, and so on and so forth. Thankfully, I have the resistant values, so we are able to determine the theoretical resistance if no other component had resistance. Therefore, our total equals 1 over 1000 ohms plus 1 over 100,000 ohms plus 1 over 100 ohms plus 1 over 220 ohms plus 1 over 1000 ohms. which gives us a total of 18,211 over 1.1 million. However, we aren't done just yet. We have to flip this giving us a resistivity total of 60.4 ohms. Next, we can measure the capacitance total. The equation used in resistance is the same except using the capacitance total values. With these known values, we can write out 1 over 1 divided by 100 microfarad plus 1 divided by 4.7 microfarad. This will give us a capacitance total of 4.9 microfarad.